All right, we're going to start on Unit 9. In this unit, we're going to look at convolutional neural networks. And these are one of my favorite types of neural networks, and they do some great things with image processing. And they really built what we call deep learning, where we have multiple layers of neural networks doing some really interesting things. Okay, so let's start. So we're importing our libraries as normal. Now, since we're into neural networks, we're importing these Keras libraries and TensorFlow libraries. So TensorFlow is the Google's high-powered library for doing neural networks and other machine learning things. And then Keras is a library that sits on top of TensorFlow that provides a little easier access for it. And we use that because it makes it easier for us to define some layers and stuff like that and set up our networks for things. We're going to start. So convolutional neural networks look at images and apply what are called filters to images. And this is a view of that, but we're going to look at another view here. I'm going to follow this link here to this article. And it talks about image kernels. And the first thing to realize is that images are made up of pixels, and each pixel has a value. Now, this is a grayscale image, and so it only has one what we call layer or color, and that's the gray layer. And all the values are between 0 and 255. And so I don't know if you can read the small numbers here, but this is white. The white values or near white values get near 255, 250, 246, something like that. And then the dark things, if I go into the dark here, they're much smaller. So this is like 20 or 10 or something like that. Now, as I move this, and you can do the same thing, as you move around, you get a red square both on the image on the right and on the numeric pixel values on the left. So I can kind of go over to a white area and then on the right side image, and then I can look on the left side image and see, oh yeah, all those white areas are all really high numbers, 250s, 240s and stuff like that. And then I can scroll down to a dark area like here and see, oh, these numbers are not really dark, but they're pretty dark. They're all in the 40s, 50s, and 60s. So our image is made up of pixels, and each pixel is a value between 0 and 255. Now, when we have color images, we actually will have three layers. There'll be three separate images on top of each other. One for red, RGB, red, green, blue values. So there'll be those three colors often combined. But the same thing, there'll be three values. So for each pixel, there'll be a red value, a green value, and a blue value. And each of those values will be the amount of that color between 0 and 255. Okay, now we're going to talk about kernels. So a kernel is just a small matrix or grid of numbers. And we use these as factors to multiply by on these things. So let's take a look and see if we can explain this. So look, the image on the left is an original image, and then the red kind of, it looks like a tic-tac-toe board, is actually a filter or a kernel here. And it'll be doing this kernel here. And as I move things along, here, it'll take the actual pixel values at that location. And so the top right corner will be multiplied by 0 because this is a 0. And then the one below it, the middle on the left side, will be multiplied by -1. And then the bottom right will be multiplied by 0 again. And then in the middle row, the middle one will be multiplied by -1. The very center one, it will have a huge positive value of 5 and then a -1. And so we add all these up, and it kind of shows down here. We take whatever pixel values in this corner multiplied by 0 here, and this one's by -1. There's a -1, and this is, and the middle one is whatever value that is times 5. And we add up these. So we multiply each pixel by the corresponding spot in the kernel, and then we add them all up and we get some total here. So like here, if I'm in some dark area, largely dark, all the pixels add up to a very small value like 35. But if I move this into a brighter area, all the pixels add up to a much larger thing, 256. And again, if they get above 256, we just cap it off at 256. Now, different kernels will will make images look different. If you ever used a photo editing program like Photoshop or something like that, um, you will you have probably applied filters that will detect edges or blur the images and stuff like that. And again, a lot of other photo apps now will have some sort of simple filtering apps. Often they're just changing colors or correcting colors, but again, they're doing it this way by applying a kernel often repeatedly. So here you can see the kernel is a 3 by 3 kernel grid on the left, but it calculates a single pixel on the right. So if I move this kernel here, these tend to be darker values all in the kernel, and so the average is 46. So on the right, you can see the pixel it generates is a pretty dark pixel. Where if I move this over a couple more here, now most of the pixels on the 3 by 3 kernel on the left are white, and they add up to a larger number, 232. And so the resulting pixel on the image on the right is bright. 232 is a bright white almost. Okay, so you can experiment by this, drag this around, and you can, again, these two things, the kernel on the left will move around in conjunction with the pixel that it's calculating on the right. So now you can also try different filters. So you could try a blur filter, and this will do different calculations for each thing, and it shows this calculation up here. And then as I move around, you'll see. So now you can see this is a blur. You can also do other ideas of what it's doing here. So with image processing, we used to manually have to create all these filters and try to use this to detect things. But now with neural networks, we're having our neural network learn its own filters and determine those own filters for this. Okay, so I'm going to close this and go back to our main thing. So this again shows the same sort of stuff. This little image here will show a 3 by 3 grid, and it will do a calculation, and it'll calculate one number on this area, and it'll move over and do another 3 by 3 grid. Now you will notice that the image that is resulting is smaller than the image we started with. And one of the reasons for that is that we're not able to do the edges. So often if we want an image the same size as the original, we have to pad the edges. So often we pad the edges with a bunch of zeros or a bunch of ones as we go. Or there's different ways of doing padding, but we have to add a little padding so that when we start, we can calculate a pixel for this top left corner. So in order to do that, we need the filter to be able to go around that. Another thing we will see is that now this example moves the filter over one each time, but we'll look at some bigger images and we'll shift the pixel, the filter over more, like 2 each time, and we'll see how that does. Okay, so we're going to have you do a little manual calculation for this. So I want you to open up this spreadsheet and make a copy of it. So I'm going to make a copy of it so that you can edit it. So we start with this image down below. So scroll down and look at this. When I made this, I was trying to make a peace sign, but it kind of looks more like a scary alien, but whatever. So we have that. That's our original image. And now we're going to apply different filters. The first filter we're going to apply is what is called a 2 by 2 max filter. And what that does is we look at a certain area, like maybe we'll look at these 4 pixels, 2 pixels by 2 pixels. That's why it's called a 2 by 2 max pixel. And then we'll simply find the largest, the maximum value of those 4 values. So if this were the case, the value of applying the filter here would be 150, because the largest value here is 150. And if we were to apply this filter down here, for example, to these 2 by 2 area, the largest value would be 255. So it's just the max of these. So it doesn't matter where the values are. So here this would also be 255, because there's a 255 here. Okay, so your job is then to calculate these. So we're going to start in this upper left hand corner, and we're going to look at those pixels. So I'm just going to fill those in. Actually filling's not going to work. Let me just do it this way. Okay, I'm going to look at that area. So the biggest value in those, they're all 255, so the max is 255. So I'm going to put that in the upper left-hand corner here. Okay, now we're going to use what is called a stride of 2. So rather than shifting this filter over 1, we're going to shift it over 2, and so then it won't overlap at all. So this is the next spot we're going to apply that filter. Is right there. And again, there are some 255s here, so the maximum value is 255. And so I put that one here. So again, I shifted the filter over 1 spot, so I'm going to go over 1 pixel here. And now I'm going to go over 1 pixel more to our right. So I'll shift the filter over 4, and we'll do that location. I mean, I'm just highlighting these so you can see them a little better. Okay, so of those 4 values, that 2 by 2 grid here, the largest value is 155. So this thing would be 155. Now similarly, if I were to shift this down, so if I shifted this down here and did that location, the maximum here is 100. So I went down, and oops, I was here. I went down, and that was 100. So I've done these things, and your job is to do a couple more here. So for example, gone down 4 here. So we've done 1, 2, 3, 4. So the last one was 100, and now the next one is going to be right here. Let me highlight that so you can see it a little better. Okay, and so I look at those 4 pixels, and the value is 200. So I can just enter a 200 here. And this should shade appropriately, so you can just enter the values and it will do some automatic shading so that it's easier to tell the value. So I did those. Now I can just go through. So the next one here, this would be a 250. There's a 250, and again I can look at this one, that would be a 250. So I can actually enter the next couple down. There's a 255. Was it 250 or 255? Yeah, 255. 255 and another 255. So now I'm done to this. So fill in some of this. So this is what is called a max filter, or a max pooling filter here. Now one thing to notice with the stride of 2 is that we started with a 16 by 16 image, and our resulting image is only 8 by 8, because we'll shift over 2 pixels for every pixel up here. So this cuts the image size in half. A max pooling filter cuts the image size in half as we go, with a stride of 2, which is really common with that. Okay, now we're going to apply this filter, a bunch of 1s, a bunch of 0s, and a bunch of negative 1s here, to this image here to calculate these pixels. So I'm going to apply it right here. And so again, the left columns are all multiplied by 1. The right columns are all multiplied by 0, and the middle columns are all 0, and the right values are all -1. And then again, if the value gets below 0, we just set it to 0, and if the value gets above 255, we just set it to 255. And again, we're going to assume there's 0 paddings around our image here. So let's look at this. So here, again, our filters are first, all the three left things are multiplied by 1. So that would be 255 times 1, another 255, and a 200. So I'd add all those up here. Okay, so I've got my calculator up at 255 times 255 is 510 plus another 200 is 700. Now, the next row is all zeros, so that would be 0, 0, 0. And then this row is negatives, -1, so I actually will subtract all. This would be plus a negative 150 plus a negative. So I would do a negative 150 and then a negative 100 and then a negative 150 again. And so my result is 310. And so again, with results more than 255, 255 is our max, we'll put 255 in there. So again, I've laid these out and I've gotten a 255 there. And then I can move this over now. Now when I move this over, I'm going to just move it over a stride of 1. So I'm just going to go over 1 pixel here and do that one. Maybe I'll do that. Let's do that in a slightly different color so it's easier to see. Okay, so this would be my new spot, and again, I'd apply these values here. I'd add these. These are zeros, and these are actually subtracted, and then and that should be 255 also. And then I want you, again, hopefully you filled up a couple more values here or here. So it would be nice if you calculated 1 or 2 of these on your own for this. So again, you don't have to calculate these full images, just fill in some values enough so that I can see that you know what's going on. The last thing we're going to do is we're going to take this image and apply, again, a 2x2 max filter with a stride of 2 here. So again, we're going to look at these, and that value is 255. Put 255 here. Then in a stride of 2, I'll look at these once I get, if you got that one filled in, then you could do that. So hopefully you can at least calculate one of these. That would be nice here as you fill these in. Okay, so hopefully I'll teach you a little bit of how by manually doing this calculation, how these filters are applied. So once you kind of understand that, let's look at how we set up our competitions or our things. So again, there's a couple questions you have to answer here about those filters. So answer those questions in the write-up here. Okay, and also make sure you share a link with your Google Sheet, so I can see that also. Okay, let's go down here. So next section we're going to do is this return to our Kaggle, our digit recognition challenge, and do that. These convolutional neural networks, our image processors, and our Kaggle digits are just images, and so this actually will work really well for these. So we're going to read in our image data here. We're going to set up our data a little bit with some training and some testing stuff. And for Kaggle, we also have some submission stuff that's separate here. And then we do some one-hot encoding for our outputs here. And again, this is stuff we've done before. But here, now this is the new stuff. We're going to set up a convolutional neural network with layers here. And there are a couple different kinds of layers we can do. The most common type is probably a convolutional 2D. And that's what we've been looking at before, where we're doing filtering. And generally, we do a 3x3 filter, and that's what we've been looking at. Now you can do up to like 7x7 and as small as 1x1 filters here, and then we say how many filters we want. And again, it used to be like when we were doing facial recognition, we would look at a face and try to figure out maybe 30 different filters we could apply to an image to help detect different, where the eyes were and where the mouth was on a face. Here, we're letting the computer figure out its own filters. So it might be finding edges or circles or dark spots or different things. So it is going to apply 16 different layers of filters. And again, we can change that number, but that's the number of filters, and they're each 3x3. Okay, so that's the convolutional, oops, sorry about that. Convolution 2D one. And then the other thing we use a lot is max pooling. And this is what we saw in our example, where we use a stride of 2 and we'll do 2x2 max pooling. So every 2x2 pixels, it'll just find the maximum value here. And this is a good way of taking a large image and making it smaller. Now, we can do some other things. We can do some dropouts. We're actually probably not going to do dropouts right now in this week and look at it in possibly future areas because there's actually special dropouts that are designed just for convolutional neural networks. There's also, once we get our image down to a small size, we'll actually flatten it out into a linear set of features. And then we can apply our dense layers. And so a dense layers is what we've been looking at in a traditional neural network. So let's see how this might all come together. So here's a set of neural networks. This is what's called a sequential design. So all these layers will be stacked on top of each other. We'll start with a 2D convolutional neural network, 8 filters, and each one is 3 by 3. And we'll do that again to detect even more advanced features, 8 different features, 3 by 3 filter. Then we'll do a max pooling filter. So what this does is we might start with a 28 pixel by 28 pixel image. That's how long how big our digits are. And then we'll apply these 8 filters. And so we'll get at this point, we just started with one layer because this is a black and white image. And now, after applying these 8 filters, we actually will have 8 different layers of filters here. And then on that, we will apply, again, another 8 layers. So we'll do that again. And so we'll end up with 8 layers again. Our image has still 28 by 28. It hasn't shrunk at all. But now we're going to apply max pooling. And so max pooling here, I'm just denoting it with this little grid. And that'll take this image, does max pooling on all the different layers, and we end up with an image half the size, so 14 by 14 pixels. And then we're going to do some more convolutional layers here, and we're going to do that. Now, often when we half the size of the image, in order to keep information about the image, we have to often double this number of filters. That's a general rule. So we had 8 filters before, we're going to double it to 16 filters here. And so we still have 14 by 14 images here. Now, once we get our image down to about somewhere in the range of 10 by 10 or to maybe 15 by 15, then we can flatten that image. So then we're going to flatten that image into one long linear string, and then we can apply our dense layers. And so this is kind of a traditional neural network here. Once we've flattened it, we have our hidden layer kind of like, and our output layer here. So we kind of put cap off our convolutional neural networks with a couple layers like a traditional neural network, an output layer and one or more hidden layers for this. Okay, so your job is to run this code here. This sets up our network. So this code sets up our network here, and I think this is set up exactly right now as what's in the comments here. But again, we'll often change this, so we could actually go in and change these layers at all as we want. But this sets things up. It does specify our input size when we start, and then our output size, how many. So our images are 28 by 28, and then we end up with 10 different digits as our output for this. So when we create this, it prints out a summary of each layer, and it shows how many weights, how many like what we call parameters can be modified in different spots on this network. And some of these networks can be large. So this one, and again, we'll ask you this, has the current setup has just over 100,000 weights that it modifies and can do. So we set up some of this early, our callbacks for things, and now we're going to train our network here. So I'm going to get that started. I'm just going to run this training. Now when we train, we can specify how many epochs to run, and so with this situation, it'll run through all the training images 10 times. That's 10 epochs go. And so this could take a while because there are over 30,000 images that it's training. So it's going through 30,000 images as it goes through this. Now, I've actually had to cut that down in order for this to work a little faster. So I've actually cut that 30,000 images down to just over 1,000 images that it's working on. That lets us read in these images a little faster and process them a little quicker. So it'll show our progress. So we're on epoch 2. And it's going through, and you'll see this little update showing how far you are through that epoch. here. It'll also be updating your accuracy here and your loss. So the loss is the amount of errors it has, and it needs errors in order to do learning and correct things. And then the accuracy is how accurate it is. So already it started 83% accurate, and it's already up to 98% accurate. Now, one thing we'll have to watch is that we've reserved some of our data for testing. So we don't train on this test data, so we have some validation data. So after it goes through one epoch, it will calculate our validation loss and our validation accuracy. And often our validation accuracy will not be near as high as our regular accuracy. But in this case, we're actually doing really well with our validation accuracy. So again, this will run for 10 epochs. I'll just pause for a sec. Okay, so this is almost done. We're almost at epoch 10. And again, you can do more training this, but to keep it manageable right now, I'm keeping this to 10 epochs. Each epoch here is running in my computer or on Colab, about 32 seconds to run. You also see like here, the learning rate was reduced at this point for running this. So now once this is done, here it'll show me my final accuracy for this. So here's my final accuracy here. And again, my valuation accuracy is still really quite good. I can also plot how the accuracy went. It's going to actually do a final evaluation here just to do a final test of this. So it's going to do a final evaluation without training on both and print out. So again, I was getting up to 100% of the that should say training images, and then the test images were this. So let me just change that. So it'll say the right thing when you get it. Okay, sorry about that. Okay, so and again, I can see my loss going down and my over 10 epochs, my accuracy increasing over time. And again, it's getting near plateau, so I don't know if we get that much more improvement if we ran it for more epochs. You could try it out and see, but okay. Now, if you want, optionally, you can enter this into Kaggle to get a high score. It does. This works very well with Kaggle, and this is the Kaggle data. But again, the main thing to do is go to your write-up and answer. So we did task 1, and this is task 2, talking about some of the answers here and how long did it take to run this training data and stuff like that. Okay, the last section here is we're going to look at more advanced images. We're going to look at the Caltech 101 images database here. So you can follow this link and learn more, but there are a bunch of different kind of objects. There used to be 101 objects, and now there are 257 different objects, and there are 30,000 images in this database, and they range in size from 150 by 150 pixels, so relatively small, to a little bit bigger, 600 by 400 pixels. Here. Now this is a big database and takes a long time to load, so I've cut it down to just 20 categories. So we're just going to do 20 categories here. So this code will actually load the database in here. And again, this is going to take a while to run, even though I've cut it down significantly. And again, in order to get it to fit in Colab, it does. And once I've got that, I can actually display some of the images here. So here's some of the images. So these are all images of dogs, and here's images of ferns. So those are two of the categories that are out there that are available. And so, and once this loads in, let's see, you can actually see the data. It'll be over here in our file under Unit 9, 10. There'll be a folder created for that, and then the Caltech data will be here. And like this is the training data. And again, there's category 51 is cowboy hats. So there's a whole bunch of cowboy hats here that I can look at. So there's no real easy way to view these here. You can download them and then view them. I'll just show you a sample image here. So here's one of the images of a cowboy hat here. So again, these are just color images that are out there. Okay, so once we've run this code, we've downloaded all the images into our Colab notebook here, space. And then we can do the normal stuff. We can run this, set up our checkpoints, And here we're going to set up a different way. Keras has a nice way of reading images from image files from folders. It assumes every folder is set up with images. Each folder, each category has its own folder. So all the dog photos are in the same folder. And again, over here, if we were to look, all the dog folders would be in a folder called dogs, and all the cowboy hat images were in a folder called cowboy hats, and all the fern images are in stuff. So this is actually some code, and I'm not going to go into too much detail here, that will set up what are called image generators, which will read and do some nice manipulation to some of these images. So a couple things it does: since the images are different sizes, it'll resize all the images to a set size. In this case, I'm just picked 224 by 224. Later on, some of the neural networks tend to like that, and so or are trained, or some pre-built ones are set up to that size. So I'm just using that as an example size. So all the images are resized to 224 pixels by 224 pixels. We're also doing rescaling the images. So if you remember, each pixel was a value between 0 and 255, but neural networks like a value between 0 and 1. So we're taking every pixel and dividing it by 255 to scale it. We're also doing things like adding a random horizontal flip every once in a while. And there's other things you can do to these images if you need to, but we're not. So most of this code is commented out here. You'll see these little comments out. So we're not doing so. And there's more features here. And again, we'll see this more later on. But I was just using this code from somewhere else, and I just left most of this here so you could see it. Okay, so we're setting up these images. These are color images, and we're doing it by category. So that's all set up. So I've run that. Now here, this is what you'll be changing: the neural network definition. So these are our different layers. So we start with an image that's 224 by 224, and our output value is 20 different categories. And again, we have a convolutional 2D layer with 10 filters. We have another one, 10 filters, and again, these are standard 3x3 filters. We do max pooling, then we do 16 filters and 16 filters, and then max pooling, and then 32 filters and max pooling, and then 64. And so notice the number of filters are increasing or doubling after every max pooling. And again, you don't have to do that, but it's a standard way of trying to keep the right amount of information. And then once you get down to some layer, we'll do a flattening and a dense layer, and then our output layer. So once you define this and run this, let me just run this. It'll print out a summary, and it'll also show the size of your image. So we started with our image, and then after our first convolution, we're down to an image that's 222 by 222, and then we do another convolution, it's 220 by 220. Now, you'd think this shouldn't be changing sizes, but because of the edges, we're losing 1 pixel around the edge each time we're doing these filters. Now there's ways of doing padding, but right now I guess I'm not doing padding. So each time I apply this filter, it's just getting a little bit smaller. But then when you do max pooling, it's cutting this in half. And then we do a couple more filters, and then we do another max pooling, and so that cuts this image size in half. So now our images are 53 by 53 here, but now we have 32 layers of those here. And again, another max pooling, and so we're down to 25 by 25 or 23 after a filter. And then we do another max pooling, we're down to 11 by 11. And so generally we try to get the images down to a small size, like 10 by 10, 15 by 15, something in that range. And then we can flatten the image and apply our dense layers. Now, the reason why we have to get these down so small is that when we flatten our image and do these dense layers, these require lots of connections here. So we need to get these images down small enough so that the number of connections in this dense layer is manageable. And so even so, there are 2 million parameters in this network that we have set up. So again, once you set that up, and again, we'll have you come back here and change some of these values in a little bit. We can train this network, run this thing. Now, I'm not going to run it because training takes a while, but right now this is set up. So it is set up to train on 50 images at a time, and then 20 epochs. So it'll go through those 50 images 20 times. Now, this is actually, I think it is actually 50 batches, and right now I think each batch is 8. So it is actually doing more than, but you can consider this the number of images or the amount, a measure of how many images it's doing uh, in each epoch. And then we're doing 20 epochs here. And so you can see this runs, and so this is running. It's only taking about 30 seconds to do this. But again, if I run this for 20 epochs, that's 10 minutes to run this training for this. And then I can plot the results here and to get some sort of results. And I can see my accuracy is going up. It looks like I should be training it more. I'm only up to 80%, and I don't see a plateau. So I could probably be training this for maybe 50 epochs or something like that. Okay, so your job is to make a couple changes to the network structure. Try to run it the way it is. Like right now, I'm getting, what's my best loss here? My final loss was, accuracy was 81% on the training data and only 70% on the validation or testing data. So 70%. So your job is to try to increase that in different ways. So you can try changing the number of filters, adding more convolutional layers, trying larger or smaller filters, trying more max pooling filters. So again, we can go back up here where we define our network here. Here's our network here. And so maybe I said, well, maybe I want less filters rather than more. So I could switch this to 4, play only 4 filters here. And then double to 16, and then maybe double to 64, or no, maybe my lucky number is 55, and here I want to go to 100 or something like that. And then run this, and you can kind of look at your summary here. So look how this goes and how many. So now I'm down to only 3 million parameters. So this should train a lot faster. So now I can go down and train it and see how fast it'll train, and then how accurate it will get for this. And then you can go back up here and try something else out. Here you could maybe we want to do more. Maybe I want to do more convolutional layers. Some of these network structures have close to 100 different layers. So maybe I want to just keep duplicating some of these layers and have 3 convolutional layers between each max pooling layer here, something like that. And maybe I want to go. Right now I'm getting down to 11 by 11. Maybe I want to try to do that even finer here. So maybe I want to do another convolutional layer with some filters in it to really convolute this, or get us down, and then do another max pooling layer. Oops, let's grab that. And for the last 10 years, researchers have been trying all sorts of different networks, and in a little bit we'll look at some of the very complicated and stuff, but they've developed some really amazing networks by trying out and experimenting different things like this on our networks. So again, now I can run this. Let's see, is my training still running? I'm going to have to stop my training, it seems like. So looks like I'm not, well, it's improving a little bit, but okay. Okay, so now I should be able to run this network structure. And again, I can look at the summary here and see how it's working now. I'm getting down to my final layer is only 200 by 200. I mean, 2 pixels by 2 pixels. So I'm guessing if I were to train this would actually not work very well because I'm losing a lot of data. I'm getting down to just a little small grid here. So, but who knows? You could try. One thing people found by experimenting is that we're doing 3 by 3 filters, and they found that sometimes 1 by 1 filters did some really interesting things and led to some really interesting results where you would not think that would be useful at all. Okay, so your job is again to just do 2 different changes here, and in the write-up try one different change and then tell you the results. Describe what the changes is, one or more changes you made, and what the results is, and then do another change and another results. Okay, sorry this was so long. I really love convolutional neural networks. Hope you enjoy this week.